All right. All right. Okay. So I'd like to thank the organizers for this opportunity. Um, I will talk about two different quantum Monte Carlo methods, and I'll probably be very brief on each of them, and I'll be happy to answer questions later. So I'll not have a lot of time on laying out the motivation and so on. So the first one is what we call configuration interaction Monte Carlo, and this is the group of people that I'm working with on that. And the second one, which is a little bit more speculative at this point, for the lack of a better name, I'll call it Lefschetz thimble Monte Carlo, and I'll explain what a Lefschetz thimble is. And this is the other group of people that I'm working with on the Lefschetz thimble. So, okay, so what I'll try to do is try to ask two very simple questions and try to see if I can give relatively simple answers to them. And the first question that I'll ask is the following. Suppose you're given an interaction which is non-local in real space. Our motivation is chiral effective field theory, but I mean there are many other situations where you get non-local interactions in real space. Given that,
what do you mean by non-local?
It's non-local in real space. So V, R, R. So if you have something like this doesn't have a, this is not, this is not true. So if you have that, you cannot write down, at least standard diffusion Monte Carlo doesn't work. I mean, you need locality. However, we know that standard diffusion Monte Carlo is very, very accurate. So the question is, can you do something like diffusion Monte Carlo, but in a different space? So if I give you a sort of arbitrary interaction in a given basis, can you do something like diffusion Monte Carlo? And we'll see that as a byproduct of that, we will also be able to do a sort of variational coupled cluster theory. These things aren't related, but I'll explain how they work out. And this is quite important because coupled cluster theory is is at least believed to be quite accurate, but the energies that come out of coupled cluster theory are not variational. I'll show how you can get variational energies from coupled cluster theory. And finally, there's an additional benefit. We can get momentum distribution in this method. The momentum operator is diagonal, and like we'll do it in momentum space. It's diagonal, so it's much easier to calculate momentum distributions. So that's the first part. Okay, so this is the layout. You've given me a Hamiltonian which has this form. There's a one-body part, a two-body part in some basis. And here, alluding to the previous talk, I'll assume that I don't know, I'm completely QCD ignorant, effective field theory ignorant, and renormalization ignorant. So I don't know, I'll not ask how we got to this Hamiltonian. Again, as I said, the motivation has been effective field theory, but for the time being, I just have this Hamiltonian. The important point to note is that there is a cutoff here. Okay, so it's in a finite basis. There's a cutoff in the number of single particle orbitals. In principle, there can be 3 body forces and 4 body forces and so on, but right now I'll just stick to 2 body forces. Okay, so the first thing that you can do is you can say, okay, I'll take this and do a full diagonalization this is full configuration interaction, FCI. Okay, so if you do that, the problem is the many-body Hilbert space grows exponentially with the single particle basis size. And this is sort of just shows this exponential growth. And soon you just hit a wall. I mean, I think right now we are somewhere here, if I'm not mistaken. We can go up to 1 billion. We can diagonalize matrices which are of the size of 1 billion, but beyond that we cannot do FCI. So can we do something better by using stochastic methods? So as I said, you cannot use standard fixed node R space Monte Carlo with these Hamiltonians. The question is,
no, but you can apply Green's function Monte Carlo.
Well, I mean, this guy is non-local in our space. At least I don't know how to do the standard Monte Carlo, which relies on locality for a Hamiltonian like this, which is written in an arbitrary basis.
Okay. I think what Mel means, right, Green's function Monte Carlo applied to lattice models, you use a C minus H as a propagator. It doesn't care if it's not local in real space, right? It's basically what you're going to do.
Mm-hmm.
You're going to keep a basis.
Yes. Well, yeah, I'm going to do basically Green's function Monte Carlo in a discrete basis. So it's just I'm just saying that it's different from coordinate space diffusion Monte Carlo. That's
just objecting to your statement, or the implication that you cannot work in R space with a non-local potential.
It's a standard.
I think it's.
I said standard. I said standard. Standard. That's the operative word.
Depends on what your standards are.
Yeah.
My standards are very low. They're very low.
There's a cutoff in a standard.
It's very, very low standards. So what we'll try to do is try to formulate diffusion Monte Carlo in a CI space. By CI, I just mean a basis of occupation number basis. Okay, so I think this is known to pretty much everyone in this audience. What you do in diffusion Monte Carlo is you use the power method. So you have some propagator, you apply it many times on some initial state, and if this state has a non-zero overlap with your ground state, you eventually project it out. Okay. The difference here is that we are going to use the occupation number basis. This is the walkers, so to speak, are just a bunch of ones and zeros. They're either occupied or unoccupied. And what we want to do is we want to interpret the transition matrix elements of this propagator in our occupation number basis as probabilities. Okay. If it is a CI Hamiltonian with a finite cutoff, then you can always use a propagator which looks like this. I mean, as long as it has an upper bound, the energy is bounded on the up. You can use this choice. This is a very simple choice. You can use this. This is, and all for the rest of the talk, I will assume that I'm using this propagator, okay, because it's just easier to explain things with this. However, this is very inefficient. We don't use this propagator. We use something more efficient. It's an exponential propagator. In fact,
Why is it? You're going to explain why it's more efficient?
the exponential?
No, the 1 minus delta tau h.
Yes, because it depends on the largest eigenvalue of your many-body Hamiltonian. I mean, your delta tau is related to that, and if you go to larger and larger systems, you need smaller and smaller delta tau.
Well, then there's tricks to it. Well, maybe that's
Well, we are going to use this operator we are going to use your trick, essentially. The trick that you came up with. So, we can use an exponential operator. We are going to use that. But as I said, I'm just going to use the simple linear propagator for illustration. So this is the basic idea. You have the propagator, and if you think about one time step in imaginary time, you write it down, you just expand it out in terms of the bases, and you finally have this form. And so this part here is a transition probability is normalized, and this other part, which is the normalization, that just gives you a branching in Monte Carlo. That's how we're going to do it. So you'll give me, I'll represent this part here at any given imaginary time step as an ensemble of walkers, and each walker is basically just a string of ones and zeros. And these transition matrix elements just flip zeros and ones, that's all. And I'll use these weight factors to use, either we can do branching or we can just keep the weights and so on. You immediately notice that what I'm calling the transition probability, it can be negative. If the matrix elements of this Hamiltonian, the off-diagonal matrix elements, if they're positive, then this transition probability can be negative. And then it's not a probability at all. I cannot interpret it as a probability. I cannot do Monte Carlo. And well, that's basically the sign problem in this formalism. And okay, so yeah, that's a manifestation of the sign problem. So if you look at a generic Hamiltonian in the second quantized notation, you will have a sign problem. There is an exception I know of, which is the pairing Hamiltonian. In that case, there is no sign problem. You basically map the problem to sort of pairs which look like hardcore bosons. But in general, there'll be a sign problem. Okay? And the idea is, can we construct non-negative propagators, and get around the sign problem? This is analogous to what we do in coordinate space, where we do that by imposing the fixed node constraint.
Can I ask a question?
Yeah.
Can you go back?
Yeah.
See, when you take those matrix elements,
Yeah.
the projection, all matrix elements which are apart from the diagonal are matrix elements of the Hamiltonian,
Mm-hmm.
nothing else.
Yeah.
So then you have an initial state, and which is typically a bad guess,
Mm-hmm.
and you actually want to go down.
Mm-hmm.
So those are the positive matrix elements which you are going to choose, and you're going to throw out the steps up. This is what you're going to do. If you're going to go from your state, you see, to a state of higher energy,
Yes.
you're going to have a negative matrix element.
Yes.
If you're going to go to lower
Mm-hmm.
energy, you're going to have positive
Mhm.
matrix elements. So what you're going to do with that?
I'll show you what I'm going to do. So you cannot just throw away the matrix elements which are positive. If you just do that, that gives you a very bad constraint. You need to do something clever. You need to come up with a trial wave function, an importance function. And I'm just going to show that in the next slide, essentially. Okay. So the difference between continuum and this is that here the basis is discrete. So imposing a fixed node type constraint is a little bit trickier here. But I mean, this question has been answered. I mean, you can do if there's something called lattice GFMC, where lattice Green function Monte Carlo, which also works in a discrete basis. And we know how to impose fixed node constraints there. The idea is you define you choose an importance function. Okay, and I'm not going to go through the details of that because that's fairly well known. You essentially choose an importance function, which I'll call phi g. Okay. You define a new propagator, okay, with the help of this guiding wave function. And this new propagator, you can choose this new propagator to be positive definite, or I'm sorry, non-negative. Now, if you do that, you obviously have to sacrifice something. And the sacrifice is now.
I'm sorry, in what sense is this an importance function?
The importance function is here in the phi g.
In what sense is this an importance function, and do you use importance sampling?
Let's see. I was not going to go into the details, but this is after then. So this is the new Hamiltonian.
Yes.
You choose a Hamiltonian which looks like this. So your original Hamiltonian was this guy, okay? And you choose a new Hamiltonian whose matrix elements are given by this.
And are positive.
No, the Hamiltonian is not positive, but the propagator is not positive.
Okay.
Okay, and this is where the importance function comes in. You can call it the guiding wave function. You can call it the trial wave function, or whatever. It doesn't matter. Basically, you choose a wave function that you think is a very good guess for your ground state wave function.
Yes.
Okay. Now you define this new Hamiltonian,
Yes.
and you define a propagator with this new Hamiltonian in the same way. Then you do your propagation with this propagator.
Right.
This is non-negative. Okay. You can show that if this Hamiltonian is exactly your ground state wave function, then this gives you the propagation is exact. Otherwise, you still have an upper bound. The energy that you'll get will be an upper bound.
No, but this is not importance sampling. You're solving a different problem.
No, wait, it's like when in diffusion of Monte Carlo you have a Green's function and you just multiply by psi
Yeah.
In order to get a distribution that is it's the same.
It's really the
Just
same thing. The,
translated in
the propagator really is multiplied by psi and psi inverse on two sides. That's really what you're doing.
The thing in the summand is exactly what you.
It's exactly that.
It's
This is
exactly
what you
that.
have. It's really important sampling.
Plain important sampling in diffusion Monte Carlo.
Okay.
It's just that the fixed node Hamiltonian is a little bit more complicated. You have to put certain things in diagonal to recover your upper bound property. But otherwise, it's really the same thing.
Sorry to.
I think
Okay.
for the purpose of explaining the method, if you just call it momentum space Green's function Monte Carlo, I think a lot of the objections would come away.
Yeah. Well, but
Pardon me?
it is, it's
Yeah.
I mean,
Green's function Monte Carlo done, if you ignore the R's, you just think of momentum.
and in a discrete space, yes.
Yes.
It's very similar to lattice Green's function Monte Carlo. There's no difference in formalism between this and lattice Green's function Monte Carlo. The difference, and I'll come to that right now, is how you choose your trial wave function. I'll refrain from calling it the importance function.
It is important.
It is an important function, so you have not been trained to call it like that.
So yeah, and the point is, if you choose a better, the better your approximation is when you choose this trial wave function or the importance function, the better of an approximation it is for the ground state wave function, the better is your upper bound. Okay. And the other point is, like regular diffusion Monte Carlo, the energies that you get from this method will always be lower than the variational energy that you had with the importance function. Okay, so the DMC energy is lower than the variational energy. That you can always show. And I'll come back to this result later on. Okay, so the question is, of course, we have all the formalism, but the main trick is to choose good importance functions, because if your importance function is bad, your energies will be really bad. So you want something which approximates the ground state wave function. Well, I mean, this is everybody's criterion for a good importance function. They should be accurate and flexible. By that I mean they should be able to capture at least the dominant correlations in your system. That's one. But secondly, they also need to be calculable. You should be able to calculate them on a computer in at most polynomial time. That's by a polynomial in the size of the basis or the number of particles. In R space, we have exquisitely accurate importance functions. In CI space, this hasn't been done, so we're just starting to do this. We don't have a lot of experience on how to write down these wave functions. One important point to note is that if you just take an R space wave function, like a Jastrow-Slater or let's say a Jastrow-Slater, and you just say, okay, I'm going to do a Fourier transform. So I'm going to take the Jastrow, do a Fourier transform in momentum space or in CI basis, it doesn't work. I mean, it gives a horribly complicated thing which is very difficult to sample. Okay, so you cannot just do that. The point is, but we do know that there are certain wave functions which work quite well in CI. The question is, can we get them to work in the Monte Carlo algorithm as our importance function? Okay. Can we sample them efficiently? So the first thing we tried was this antisymmetric geminal power wave function. So suppose we have an even number of fermions, okay? And then the way you write down an AGP wave function is you create essentially a two-body wave function, and you operate that n times. So you're treating your final n particle wave function as a combination of two particle wave functions. So you have a two particle wave function, you operate that n over 2 times on the particle vacuum. That gives you the AGP wave function. And you're free to choose whatever you want for the two-body wave function. That's why it's so flexible. If you have an odd number of particles, you just put an extra odd particle out here. So the good thing is this guy, if you want to calculate the overlap between this and any walker in R space, for that matter, any configuration in R space, this is a Pfaffian. And there are we know how to calculate Pfaffians. There are very fast algorithms for them. So that's why they're quite flexible and they're quite good. So I should point out that things like Hartree-Fock-Bogolyubov, BCS, and Hartree-Fock, all these are special cases of this general type of wave functions. Okay.
They are not. One of them has fixed particle number, the other one has not.
Sorry, it should be particle number projected. So it's PHFB will be, or PBCS are special cases of this. Yeah, you're right. So this was okay, you can't really read the axes, but this was the first application. This is the first place we applied this method. It was you take a unitary gas in a trap, unitary gas of fermions in a trap, and the interaction is just between up and down spins. Okay. That was the system. And in this case, the good thing is that these AGP wave functions, if you want to calculate the overlap, they're just determinants. It's not even a Pfaffian, which is even simpler than calculating a Pfaffian. Here, what we plot is the energy, the ground state energy, from our estimate for the ground state energy as a function of the number of particles. And as I said before, see, Hartree-Fock BCS and PBCS and PHFB, these are special cases of AGP.
This is very the opposite of what you start out as. Not only it's non-local, but it's actually a delta function. It's a local.
What is local? I'm sorry.
You're an interaction then.
Yeah. So you're absolutely right. So I should clarify this. So the cases that we have applied this method to so far are all for local interactions, simply because for the purpose of benchmarking. I mean, we want to see how they compare with other methods, and you need local interactions for regular DMC to work. So that's why.
But you put them on a lattice and then it's normal. With a
If you
yeah.
You can construct model problems with genuine non-local interactions.
we are doing that. So that's in the process. So we just wanted to benchmark things first, and just to make sure that we are in the right ballpark at least. So this is the energy as a function of n, and here I have 3 different plots. So I have Hartree-Fock, particle number projected BCS, and particle number projected HFB. All 3 of them are examples of AGP. And we expect, you would at least naively expect, that HFB will be better than BCS or Hartree-Fock because it includes both mean field and pairing correlations. And we see that. See, the bottommost, the lower line is HFB, PHFB, and the 2 upper lines are BCS and Hartree-Fock, and it is significantly lower. So it really means if you have good wave functions, you get good energies. I mean,
actually, what's the difference between HFB and BCS projected?
The HFB also takes into account the correlations in the particle-hole channel. So BCS will only take into account particle-particle, the correlations in the particle-particle channel.
For this model, if you have a unitary, if you have a negative
In a trap, they are different.
Yeah, in the trap they're different. This is the trap, yeah. So the mean field is non-trivial.
Yeah, the Hartree part.
Yes, yes, that part is non-trivial. Here we compare. So we also compared our results with exact calculations, like exact diagonalization in small bases, and there we see that the error is of the order of 2 to 3% with the PHFB wave function. But then we compared results with other Monte Carlo calculations. Actually, here we should also have results by Stefano and others. I mean, their results are slightly lower, I think, than these guys, but that should be added. So these are calculations with, we did calculations with 9 oscillators. This is in a harmonic trap, so we did calculations with 9 oscillator shells. We saw that at that point, our energies didn't vary by much. The variation was less than the error bar. And the other 2 calculations are by fixed node diffusion Monte Carlo or fixed node Green's function Monte Carlo calculations. And you see that the agreement is very good. If you compare actual numbers, again, we are off by, with the real space Monte Carlo calculations, we are within about 2 to 3% in energy. Keep in mind that our wave function is still not optimized. I mean, we just take HFB, HFB. I mean, in principle, you can optimize this part much more. I mean, HFB is probably not a very good approximation, very good wave function at unitarity. This was just a first try.
Sorry, but is it a problem of nodes, or is it a problem of finite basis?
No, we just did not do the optimization. We just took PHFB and said, okay, let's see what energies we get. In principle, you can do much better. You can, for example, say.
So you get this difference to the wave function.
Pardon me?
To the nodes.
For the nodes, yeah, the nodes will be different. You can say that this part I'll just solve the 2-body problem and then put that in here, or you can take a combination. You can do many things there. And this is the calculation for the pairing gap as a function of the number of particles. And our calculations except for this one point, our calculations seem to agree quite well with LDA calculations here. Whereas, and our error bars are also much smaller than the real space diffusion Monte Carlo calculations. But this is this should be taken with a grain of salt. I mean, I don't know how long they ran the simulations for. I mean, you can always reduce that. So, but by and large, the moral of the story is that we are definitely in the right ballpark, even without a lot of optimization. The energies seem to be quite consistent with fixed node DMC calculations for local interactions. Okay, so then we said let's see if there are any other wave functions that we can use as the guiding wave function. And one particular wave function that's used a lot in both in chemistry and in nuclear physics now is the coupled cluster wave function. Okay, it has a lot of really nice properties. I'll not go through them, but it is very popular. And the basic structure of the coupled cluster wave function is the following. You have some model wave function, typically it's the Hartree-Fock wave function, and you apply an exponential operator on it. This exponential operator will have one body part, the two body parts, three body parts, and so on and so forth. You apply it, and the final wave function that you get is your coupled cluster wave function. If you truncate this, and you would in a real calculation, that gives you the different acronyms. You can get coupled clusters, singles, doubles, triples, and so on and so forth. So this particular truncation, coupled cluster, singles, doubles, and triples perturbative, that's considered to be the gold standard in chemistry. I mean, I think that those are some of the best energies you can get. So this is clearly a good choice, at least. If we can get it to work in Monte Carlo, this would be a good choice. But one point to note is that the coupled cluster energies that you get from regular standard coupled cluster theory, they're not variational. You are not calculating in coupled cluster theory something like you're not calculating this guy. You really have HCC, H, and something else on this side. Okay, and so that you cannot prove basically you cannot prove a variational property for the energy. They can be either above or below your exact energy. It will be nice if if one can get variational energies starting from coupled cluster wave functions. Okay, so that's the question. Can we calculate these guys quickly? And turns out you can. I mean, there is a trick that one can use to calculate them. I'm showing this here with the coupled cluster doubles, which is at least a good starting point for a uniform system where you don't have the singles because you have momentum conservation that throws away the singles. So this should be a good starting point for uniform systems. And the basic idea is very simple. If you write down the amplitude, so if you write down this overlap, okay, in this particle hole language. So say I have m holes and m particles. Okay, I'm calculating the overlap. That you can write it down as a sum over m minus 2 hole, m minus 2 particle overlaps. Okay, you can write it down as this sum. And then you can just, this gives you a recursive formula that you can, so you can start, if you want to create a n particle, n hole overlap, you just start from the 0 particle, 0 hole overlap where you know the answer, that's just 1, and you just build it up from there. The scaling of this formula is, so this can be generalized to CCSD or CCSDT, it's not very difficult. The important point is that the scaling of this goes with the number of particle hole, the average number of particle holes that you have in your walker. It doesn't scale with the number of particles or the size of the bases. Okay, so it will have some scaling with how strong your interaction coupling constant is, but no scaling with the number of particles and the size of the bases. So this is very important. This is it's polynomial. I mean, it's better than polynomial. Now, so we decided to apply it to some system, and again we chose a local interaction because there we have some results, and there are many calculations which are available. So how did we chose the Hamiltonian that we chose to test this particular wave function is the three-dimensional homogeneous electron gas. So the interaction is very well known. There are many calculations. Now the question is, how do we do this Monte Carlo calculation for the homogeneous Coulomb interaction? What we did was we just constructed a lattice in momentum space, okay? And our basis is now just the plane wave basis. And we
I'm sorry to interrupt.
Yeah.
It must be on the previous page. The statement is you can calculate
Yeah.
you can calculate its inner product
Mhm.
of a configuration in momentum space.
Or any CI space, yes.
In cost, order,
Order the number of particle holes in your in that configuration.
order the
Not order that. I'm sorry. It's a function of that. It's a combinatorial function of that, of the number of particle holes in your configuration. But that number does not scale
Can
with.
you go to the formula which you wrote, the recursive formula?
Yeah.
So let's assume I have only doubles. Then Fm actually goes all the way from 0.
Mhm.
It's from 0 to the total number of sides I have.
Mhm.
So if I calculate to see how many amplitudes I need basically an exponential number.
Total number of.
Sides.
Total number. No,
Every
yes. Okay. Yeah.
number
Yeah.
has
Yeah. Yeah.
sides.
That's a very good question. Yes.
Yeah.
So
That
the.
number is not polynomial. It's
No.
actually the size of your Hilbert space.
Yes. That's true. But the point is, most of the time, most of your walkers, an overwhelming number of your walkers will always have a finite number of particle hole excitations. You once in a while you will get hit by a walk.
It's weak.
Sorry?
If the interaction is weak, it doesn't mix very strongly the states.
No, even if the interaction is strong,
No.
the average number of particle hole excitations in your system is not. It doesn't scale at the number of particles or the base size of the bases.
Wouldn't that,
It's much worse than that.
so you would still, so you have an effective Hilbert space which is much smaller than the original Hilbert space, is that what you're saying? But it's still exponentially large, isn't it?
Yes.
No, I don't have an. It's not the Hilbert space. Okay, so
The number of coefficients that you have to calculate,
yes.
how does it scale with n as n goes to?
No, so there is no scaling with n. That's my
It
point.
scales with the number of sites in the lattice.
It does not scale with the number of sides of the lattice either. You can no, you first of all you cannot create more than it can at most be n, right? I mean you cannot create more than n particle n hole excitations, where n is the total number of particles in your system.
I know, but you have to consider all possible combinations. Suppose
Yes.
you created p of them,
Yes.
wouldn't you go with x e to the p?
Pardon me?
I mean, wouldn't, I don't know.
No, so that's the the question is what is the average number? Suppose you have an ensemble of 10,000 walkers, okay?
10,000 particles or?
10,000 walkers. So 10,000. The size of the ensemble is 10,000.
using the
Yes.
structure, right? You
Sorry?
You can just address one, you're trying to do the scaling weighted by a Monte Carlo population.
Yes,
I
yes.
think people are just saying, don't do that, consider a particular type of, it's possible that you have.
No, yes, it's possible that you can have one walker
Yes.
which will where the number of the particle excitations is of the size of the number of particles or very large. But
Then
on an average, sorry?
Then the scaling is what?
Then it just scales it has a combinatorial scaling with that. But that's one walker. On an average, you will be calculating quantities, on an average, if you take an average walker out of your ensemble, the number of particle hole excitations for that walker will be a finite number. It doesn't scale with n.
Let me give you the argument in a different way. I'll
Mhm.
take the unitary gas.
Yes.
The unitary gas, the interaction is strong.
Mhm.
You populate momentum states all the way to infinity. The momentum distribution goes like 1 over k to the 4. So it decays extremely slowly, very long tails.
Mhm.
So basically, it's the entire Hilbert space.
It's
So in that case, you see, you don't talk in terms of walkers. You see, you have to populate the entire space, and then you're screwed.
so yes, I agree with you that if your interact the
Your
str-
argument doesn't go in that case. It goes only if the interaction is weak.
no, okay, if
Then, I mean,
Even
how
then
do you
it's
get
another
size
question.
extensivity without having more excitations as you go? I mean, you have a single unit cell, right?
yes,
You have an excitation, say
Mhm.
1 hydrogen.
mm-hmm,
Now you have 2 hydrogens,
mm-hmm.
and the excitations you should be able to excite both hydrogens the same, right?
But that doesn't have anything to do with. I mean, that's a completely different question.
No, the question is, how does your scaling go with system size?
That's the point I'm making. That yes, so there's definitely a very strong scaling with how strong your interaction is. If the interaction is strong, the stronger your interaction is, the scaling will get worse. I mean, that's beyond, because the stronger your interaction is, the more of the Hilbert space you're going to populate, and the average number of particle hole excitations that you'll have will become larger and larger, and this scaling will get worse and worse. There's no question about it. However, the point is, this scaling for some finite coupling doesn't have, at least in the thermodynamic limit, it doesn't have a scaling with the basis size and the number of particles.
You can fix RS in the electron gas, and then ask how the things get worse as the basis goes to infinity and the number of particles goes to infinity.
Yes, and in that case,
I mean,
if
you kind of confused me because on this graph you say it doesn't depend on the basis set, and then on the next view graph you said, well, I'm going to fix the basis set. Right. So that was why do you put in a K max if it doesn't depend on K max?
oh, so this does not depend on K max, but let me go back here. Here you see you have a sum. And so the way you do the propagation is, suppose I start from one Walker, one configuration, and you need to figure out what will the next configuration be. So what you need to calculate is all the connected matrix elements with this one configuration, and that has a scaling with the basis size, because you have to look at the interaction and see how many configurations are connected. So that's that has a clear scaling.
You do that analytically or something, and you wouldn't.
In general, if you give me a horrible interaction, there's no way to do that analytically. So I'll just have a list of matrix elements, and that scaling, if you have momentum conservation, is scales linearly with basis size. If you don't have momentum conservation, is omega squared, n squared, something like that. So yeah, there is obviously the method has scaling with basis size. I'm just saying that this particular matrix element doesn't have any scaling. But yeah, it gets worse and worse with as you make your coupling constant stronger and stronger. If you go to strongly interacting regime, it will be much worse. I completely agree with that. Okay. Yeah. So coming back to this, yeah, we just choose all the single particle states up to some maximum k max square. So this is just putting a cutoff in energy. So this is an example of the kinds of calculations we're doing. So here you have basis size. This is the single particle basis size. This is not the many body Hilbert space. This is the size of the single particle basis, and these are the correlation energies. You see, there is some level of convergence, but at least in this particular work, we did not attempt to do any extrapolation in the basis size. My feeling is that one should probably not use the bare Coulomb interaction and just try to go to larger and larger basis sizes. One should probably use a more effective Coulomb interaction. But so this is essentially what we get.
Do this for large RS?
We do this for up to 3. We tried up to RS equal to 5, and we could do small basis sizes. But as we go to large basis sizes, we are still doing that.
RS small is perturbative. It's RPA result to give the energy basically.
For RS equals 3 is not perturbative.
Well,
Where RPA is very fast.
Yeah, I mean, yes, I mean, as we go to large.
are no problems. Big
But
RS
small means less than 1.
Yeah.
I agree. RS of 1 is kind of a dividing line.
How bad is RS equal 1 in RPA?
In what?
How bad is it? It's worse than 5% or not?
For what method?
RPA.
Oh,
RPA in RS equal 1.
I don't know.
I think it's within a few percent there.
Yeah.
So yeah, we are trying to do larger RS, and as I said, we can do calculations, and as it definitely we need more computing time. There's no question about that. As we go to larger RS,
Can you say how you get by the sign problem? I kind of missed that. You said
by the sign problem,
Yeah, you said you changed your propagator.
it's a fixed node. We
I see.
basically choose a we managed to write an Hamiltonian for which the propagator doesn't have a sign problem, and that propagator depends on your the wave function you choose, and the better wave function you have, the better energies you'll have.
So that was how many electrons that you were looking at?
These calculations, these are for 14 electrons, but we have also done calculations for 38 electrons and 54 electrons.
But this is a different fixed node than if you're doing it in real space, is that?
Yes, the constraint will just look different. I mean,
Although, in the basis set limit, this is a question actually. expect it to become the same if you could implement it for if k max goes to infinity?
Implemented
Well-
still in the k basis or in a lattice, like a lattice side basis? I mean, okay.
It's K in the continuum.
Sorry?
So you could, in principle, we have done
Yeah.
K in the continuum, so you could do that.
No, we can't. I mean, we still have a.
You could. One could. One has.
No, wait. Continuum in this method. I mean, here I need a finite basis.
You need QCD for that.
Yeah.
Why do you need a finite basis?
I need a finite basis because when you calculate when you try to calculate a move, you have to calculate all connected moves, all the connected matrix elements with a particular.
If k max goes to infinity, at some point you can do it analytically or
Yeah.
something.
Yeah, I mean,
No, so for a simple interaction which is local and which has a very simple property, probably one can do that.
This is a simple case.
This is a simple case, but we are trying to develop the machinery for more complicated cases. And there you just have a bunch of matrix elements. I mean, it's difficult to see how you can just go to the infinite basis size
I understand.
analytically.
In cases where you can, where you can do this, where you can write a normalized probability density down,
Yeah.
then you can be in the continuum.
That may be possible. I mean,
It is possible
I mean-
for certain interactions.
okay, for the Coulomb it may be possible. As I said, we're just trying to develop machinery for non-local interactions, for which I will actually not show you any results, unfortunately. So, okay, we see that if we just use couple cluster doubles and then project it with this Monte Carlo, we get about 95% of the correlation energy in a fixed basis. And okay, here I am using the FCI QMC calculations as I'm taking them to be the benchmark in the fixed basis homogeneous electron gas case. With respect to those, we get about 95%, and clearly one can do better by including triples and so on here. As I said, I mean, this wave function doesn't have any adjustable parameters. I mean, it's just a couple of clusters. And we can improve systematically.
How do you justify that, the accuracy being comparable to our space?
Well, if you look at the DMC, the fixed node DMC calculations for the couple of calculations that are available, the latest calculations, that compared with the extrapolated FCI QMC calculation is about something of that order, couple of percent, and we are at the
space ones use probably 1 million times less computer time and are much more accurate, I would say.
than the FC.
Showing, yes.
I don't think they use as compared to what we are doing, or as compared to FCI QMC.
They were done 30 years ago.
No, I'm not talking about those calculations. No, I'm not talking about those calculations. I'm talking about the more recent calculation.
Oh, I thought that second line, accuracy comparable to our space.
But there are more recent R-space calculations for the homogeneous electron gas. That's what I'm talking. Those are the ones I'm talking.
Those are backflow.
In any
With
case,
backflow, yeah.
The point here is not, once again, the point is not to do the calculation for the electron gas.
Yeah.
The point is that you want to do these calculations for other
Yeah,
calculations.
yeah, so-
it's
I
obviously.
just don't think that statement is true.
Yeah, okay.
Well, okay. So the point is not that if
Like comparable means. but-
Yeah.
so
And backflow was done a year after.
no, but there are more recent. I don't have the reference here, but there are more recent calculations which in the past few years for the homogeneous electron gas.
Right.
And I'm just talking about those calculations. But okay, so let me be very clear. I am not making the statement that if you have a local interaction in R space, you should be using this method. It makes absolutely no sense.
No way.
Yeah, I mean that's ridiculous. Only if you have a method which is non-local, where it's not very convenient to use R space diffusion Monte Carlo, then you might want to use this method. Okay.
Can I ask just one more question?
Yeah.
Mr. So even older calculation was Bishop's original couple cluster. How much more energy do you get over the initial Bishop couple cluster?
Bishop's coupled cluster for homogeneous electron gas.
Yeah.
We haven't compared with coupled cluster calculations. But, okay, I'll show you an example of, we do our coupled cluster calculation, and we can compare it with the CCD calculations. The one thing to keep in mind is that this point about how much do you get over a coupled cluster is not a fair question, because coupled cluster is not variational. So they can be below the exact energy. Only if two theories are variational, you can make that, you can ask that question.
But just to, I mean, in these examples,
Yeah.
you can basically have exact answers, right? Like you said, you could take for CIQMC, so you could compare.
Oh yeah, there we did. We did compare. We did compare.
In practice, coupled cluster is not variational.
Yeah.
But in theory, it's not variational. But in practice, it would come, I think.
Yes. So
Better than 95.
I'll just give you an answer. I'll just show you an example. But yes, for let me just.
Actually, the 95% is just what you get in Slater-Jastrow without even a GFMC.
Yeah. So I would say that this is something like CCD is just something like Slater-Jastrow. If you want to do better, you need to put in triples. I mean, yeah, you need to put in triples to get to that level.
But I thought you're doing the QMC so that you should be better than coupled cluster.
Well, again, like better is tricky because coupled cluster, as I said, is not in these cases.
I mean,
So
it's a fixed node with a sort of bed Jastrow wave function.
Yeah.
In a space in which, I mean, the nodes are something that includes the effect of the heavy bed percoloration somehow. It's not like in coordinate space. If you have a bed Jastrow, but I mean, the determinant is, you get a big variance, but the energy is right. Here it's more tricky, the situation, because essentially in the fixed node, you're throwing in even effects of a quotation mark bed Jastrow. So somehow it's a completely different perspective.
I'd like to take the unusual step of suggesting that we reduce comments at this point because there's 10 minutes left.
Yes.
And we have close to half the number.
yeah. Okay. So I'll go through the next few slides very quickly. Okay. So basically, what we have done is we have some formulation of DMC in a fixed node DMC in CI space, and these energies. The great thing is that these energies are variational, and they're super variational with respect to coupled cluster. Okay, this will be very nice to have, a variational energy from coupled cluster wave functions. What we have is a variational energy which is less than the coupled cluster energies. And this is a very nice result, I think. Okay, let's forget about Homer. So this is the question that you were asking. Okay, so do we really need exact coupled cluster wave functions for these calculations? Coupled cluster calculations are heavy. Can we get by without using the exact coupled cluster wave functions? And it seems like the answer is yes, because the thing that is more important is the sign structure of the wave function, not really the actual amplitudes that you put in. So here, these are the energies from CCD, the full CCD calculation. And this, what I call CCD1, is if you think of doing coupled cluster iteratively, then if you stop at the first step, it's just getting the amplitudes from second order perturbation theory, okay? And then build up the coupled cluster wave function starting from those amplitudes. I call the CCD1. So this is what you have from CCD1. Okay? Now I can do Monte Carlo either with these guys, which obviously is a much better wave function, or with these guys. And you see the Monte Carlo results are basically on top of each other. So the final result that you get from propagating with Monte Carlo is quite insensitive. The energies are quite insensitive to the how accurate the coupled cluster is. Of course, the variance is different. I mean, the variance using this is much lower. But so the claim would be that, okay, you don't really need to solve coupled cluster exactly. You can do a few iterations. If you have a strongly interacting system, then obviously second order perturbation theory is not enough. You need to do a few iterations, but you don't need to iterate it till convergence, which may be very beneficial for if you want to do CCSDT or something like that in finite systems, where these are very expensive calculations. One might be able to save a lot of computational time this way. I think I'm probably going to. Okay, let me just go through it quickly. The other thing that we could do was calculate momentum distributions, because momentum is diagonal in momentum space. And We can even calculate pure estimators. I mean, this is nice because it's diagonal in momentum space. You can use the Feynman-Hellman theorem to convert the occupation number, the expectation value of the occupation number, to an energy, basically. But then you can use a trick, this derivative that you have. Typically, if you want to calculate it numerically, you can do many Monte Carlo calculations with different values of alpha here. But taking numerical derivatives is very noisy. You see, you can even, but you don't need to do that. You can convert this. You can use a trick to convert this into a mixed estimate. This is something we can calculate in Monte Carlo. And another covariance quantity, which is something we can again calculate in Monte Carlo. This was shown earlier. I mean, this is not our work. But we use this trick. We use this trick to calculate the momentum distribution. And now this is for a Yukawa interaction. And we essentially took we fixed sort of the density and the screening length as, we took those parameters from the one pion exchange interaction and so on. So this is just for illustration. You see, the blue ones are the pure estimates, and the green ones are the mixed estimate. This is what one would calculate normally. And there's a pretty big difference near the Fermi surface. This is not unexpected. This is quite expected. It just goes on to show that the benefits of using a pure estimator as opposed to a mixed estimator. Okay.
Is it a normal system or superspace?
This is a normal system. This is a normal Yukawa system in a box in a momentum space lattice. Okay, so I'm going to move on to the next topic. Are there any questions? Or we can discuss questions later on. I mean, okay. Okay, I'll go very quickly. So this is a completely different Monte Carlo method. Forget about configuration interaction Monte Carlo. Here, what we want to do is, we want to calculate quantities like this. This is the expectation value of an observable. You have this is basically you have some sort of an action, and which depends on some fields, and you want to calculate an integral like this. This is, you see this, for example, and if you use auxiliary field Monte Carlo in many body theory, you will land up with integrals like this. And if this S is not real, then we'll have a sign problem. Okay. Now the question is, and this is defined for phi over the real domain. Now the question is, can we do better? Can we sort of soften the sign problem if we let these field variables become complex? That's the question. And turns out that yes. Suppose your the action has a saddle point, okay, at this field variable.
In the previous integral, I see, that's right.
It's over the real.
Number of phi's, okay.
Yes. So suppose your action has a saddle point. What you can do is you can shift your integral and just do an integral over. So this is now, let's think about one dimension. It's just easier to think about it. So you move here, and you integrate on this line. This is just sort of a shifted contour. That way you make the sign problem a little bit better. And then you can also try rotating it, okay, to make things better. Finally, what you can do is you can integrate over the path of steepest descent, okay, which is just given by this. Essentially, the point about the path of steepest descent is that the imaginary part of the action is constant on this path of steepest descent. Okay. So there is no sign problem from the action, and the real part of the action is bounded from below. Okay. So it's completely integrable on this. The question is, can we use this result? I mean, can it be generalized to a many-dimensional case? I mean, if you have a lot of field variables. And the answer is yes. There exists a many-dimensional generalization of this, and that is called a Lefschetz thimble. So Lefschetz thimble is basically, imagine you have an action, you move to a saddle point, and then you try to construct the paths of steepest descent in every direction you can from that saddle point. Take the union of all paths. That'll give you a manifold in this complex space. this is the Lefschetz thimble. Now you say, I'm going to do the integration here.
Why is there more than one path of steepest descent?
Because you have many field variables. You have many directions you can move.
You mean you constrain all but one or something?
No, if you solve this equation, you see at the saddle point, you can choose any direction, so to speak, to move, and then follow this equation.
Oh, I see.
And that basically just gives you the manifold. So that's the definition. You do that. The point is, it is an n-dimensional object. So the dimension of this manifold is the same as the dimension, of your original integral. So that's a very good thing. You are not changing dimensions or anything. So if you write down an observable on this Lefschetz thimble, it will look like this. You'll have an imaginary part of the action which comes out. So there's no sign problem from there. It's constant. Then you integrate over the real part. But then there is this measure, which is a very non-trivial measure now. I mean, it's not trivial, because this is a curved manifold which is defined by this differential equation. So this is not a flat measure. It's non-trivial to sample it. So I'm not going to give you any details of how we go about sampling it. I'll just give you some results to at least speculate that this may be a good way to think about things. Okay. So here, this is a one-dimensional model, the one-component model. Okay. We have an action. There's one field variable. The action looks like this. This obviously has a sign problem if you try to do it in real space. Concentrate on these lines. The dashed line is the exact calculation. This is a one-component integral, so you can just do it analytically. Okay. And concentrate on the blue circles. Those are basically the calculations on the Lefschetz thimble. So if we use this trick, going on the Lefschetz thimble for this one-component model, this is just doing it on the steepest descent, you recover the exact result. Okay. So the next question is, do you get a sign problem from this measure? Because this measure is not guaranteed to be positive definite. Okay. Do you get a sign problem from this measure? And again here, concentrate on the blue line. This is what you get for essentially the cosine of the argument of the measure. That basically tells you if there's a sign problem or not. Okay. If it's positive, then there is no sign problem. That is plotted as a function of this is actually the probability that you're sampling. And this is very stable over many orders of magnitude. Here, you see, it's absolutely it doesn't change by much. So at least for this problem, I mean, there is no sign problem. I mean, your measure is positive, and there's no sign problem from the action. Then there's something more complicated one can do. One can think of what we applied it towards the complex scalar field theory, and now this is a regular field theory with an action which has a sign problem. Okay. And we know that there's a pretty hard sign problem. Here again, if you look at as a function of the chemical potential, we have plotted it here. This is what happens. These are for different lattice sizes. These are four-dimensional in four-dimensional space, and you have different lattice sizes. You can have lattice size of 4, 6, and so on and so forth. This is what happens if you try to do the calculation in the regular way. This is basically the sign, and it just goes to 0 exponentially. See, it just goes to 0. Whereas if you do it on the thimble, you see that the sign it doesn't go to 0. It gives you a non-zero number. So you can avoid the sign problem this way. In fact, we compared our results for this is basically the density for this problem, and we can calculate it as a function of mu. The red points are an exact calculation. For this particular problem, there exists a transformation which is suited for this problem, which solves it exactly. Okay, so we have exact results, and we compared with our algorithm, which are the blue points, and you see that they agree, like they are almost on top of each other. So there is very good agreement with the exact calculation. Not only that, this particular phenomenon that you see where the density is basically 0 up to a point and then it suddenly starts rising, This phenomenon is extremely hard to see normally. If you do a normal calculation with a sign problem, you won't see this phenomenon. But on the Lefschetz thimble, if you do the integration on the Lefschetz thimble, you see it very clearly. So at least it looks like this is something that is worth pursuing. I mean, okay, so this is very speculative. So there are a couple of things I haven't told you much about how we actually sample this. As I said, the measure is very non-trivial. How do you sample that? Currently, we have two algorithms that we use to sample it. There's one which is based on Langevin dynamics, and there's another one that we have developed which is based on basically Metropolis, but with a mapping to a flat manifold. So we are in the process of implementing these algorithms. How do you actually calculate the measure? I mean, the measure will give you another contribution to your integral. To do that, you really need to calculate the Jacobian. I mean, you have this curved manifold, you have a tangent space, and you have to really calculate the tangent, the Jacobian of that. And yes, and this is the important point. Does this measure lead to a sign problem? And I mean, we don't have a proof saying that, okay, it does not. It can, in principle, give you a sign problem. But in the leading order, it doesn't give you a sign problem. You can show that. I mean, if you do a saddle point approximation, it doesn't give you a sign problem. In fact, it's 1. So it's hard to see how the subleading terms will add up to completely make the leading term go to 0. That can happen. We cannot prove that it won't. And the final question is it enough to integrate on just one thimble? I've not discussed the technical details at all, but it's not obvious that you can just take this one thimble and do the integration and be done with it. Maybe you might need a combination of a bunch of thimbles and then do the integral. We have very strong arguments in favor of saying that we can just use one or a very small number, but again, we don't have a rigorous proof. That's something we are working on right now. Okay, so that's all I had to say. Thank you for your attention.
I didn't get the details in the second part, but I
Mm-hmm.
should comment. I think what you're talking about,
Yeah.
we do implement in auxiliary field Monte Carlo.
Uh-huh.
The flat one we call a background shift.
Yeah.
The first order derivative we call force bias.
That will be the Gaussian manifold, yes.
And I think the answer to this question about the sign problem is yes, it does show up. It
So.
helps a tremendous amount, and we have a lot of data in ground state showing this.
Uh-huh.
And then eventually it'll show up. It just lessens, it reduces the sign problem, but it doesn't take it away. To leading order, it takes it away exactly.
Mm-hmm.
This complex gauge transformation cancels
Mm-hmm.
the leading order development in phase.
Mm-hmm.
But the next orders accumulate. The sign problem, anytime you have a small leaf, right, eventually it's exponential.
Yes.
Much smaller coefficient.
Yes.
But we can talk more. I may be wrong, but from what I could gather from what you're saying, we have been doing this.
So let me just re-comment on your comment. So you're right. So yes, I mean, if you just move it as just a background shift, and if you do the rotation, as you said, that'll be the flat manifold in that sense. And I suppose you're saying that you do these two things.
Yes.
But do you actually do it on the curved manifold?
Yes, we do it on the whole path, right? In the ground state, as we go on, it's dynamic. Right?
So,
it's
but
like you're defining a path
yeah.
in imaginary time on the fields, and you're saying you want to follow the derivatives.
No, this time is not related. This time is not related to the tau. Imagine this is a different direction.
You're trying to integrate a field, and I'm trying to use these auxiliary fields to propagate. So at different times, this quantity, the action, what you're calling the action, changes.
No,
time-dependent derivative. As I say, we could.
Yeah, we can talk about it, but this is a 5-dimensional. It becomes a 5-dimensional problem in that case. I mean, it just gives you an extra dimension, the imaginary time. However, yeah. So the question about whether it solves the sign problem or not, I'm fairly convinced it doesn't. I mean, I don't think this is the solution to the sign problem. Then we'll be collecting our prize. But I think it makes it much better. That's my point. Yeah, it makes it much better.
I've done pretty careful study
Yeah, I mean, I'm fairly convinced that it doesn't solve the problem. But you can go to larger and larger sizes by sort of carefully choosing your domain of integration. That's the point. So if you can go from a lattice size of 4 to a lattice size of 20, that'll be very helpful.
Okay, we are already late, so I think we could postpone further questions, if any, to the afternoon. So.
Okay.